Good morning, everyone, and thank you for joining our webinar this morning. My name's Hemi Baldock, and Alex Watson today will be giving you the webinar. Just a few housekeeping points before we start the webinar. We're kind of looking at a runtime of about 40 minutes this morning, and the event will be recorded as well. If you have any questions while we are running through the webinar, please feel free to pop them in the Q&A box down the bottom and we'll answer them at the end. Any questions that we don't get time to answer, we'll get back to you after the webinar and discuss this with you. The webinar as well will be available recorded after we're done. So I will pass you over to Alex.
Perfect. Thank you very much, Hemi. Yeah, so welcome everyone. This is the first webinar in Analytics' annual webinar series, and we're doing a number of application-focused webinars throughout the year, all free to join, so feel free to get involved in our other webinars. Today, we'll be looking at the oligonucleotide synthesis workflow with a specific focus on cleavage and deprotection. And this is really the traditional bottleneck in oligonucleotide synthesis. And today we'll be looking at potential solutions for solving this bottleneck, and we'll be presenting a milestone solution for this as a microwave-based gas phase cleavage and deprotection technique. So without further ado, let's get into some background and work towards the solution. So firstly, oligonucleotides. What are oligonucleotides or oligos? These are short, specific sequences of nucleotides, typically fewer than 20 base pairs or 20 nucleotides. Nucleotides are the building blocks for DNA and RNA. For DNA, we have thymine, cytosine, adenine, and guanine. And for RNA, we have the same, but thymine swapped for uracil. The specific sequence of these nucleotides is what denotes the function of the oligo. These nucleic acids occur naturally, but we're also able to produce them in the lab. And there's a growing trend of people bringing in oligosynthesis in-house rather than using larger external suppliers. A few reasons include that technology is just getting more accessible, more places are able to do this, and also it prevents long lead times waiting for oligos, and also the costs of getting an external company to do so. So what are oligos used for? The importance of oligos has really dramatically increased in the last decade, particularly so after the COVID pandemic. And there's a long list of applications. A couple include sort of for research. We could be ordering custom oligos to perform perhaps gene editing, or perhaps we could be ordering custom PCR primers for PCR application of specific nucleic acids or genes. There are also diagnostic applications. Again, we could be ordering custom PCRs to perform real-time quantitative PCR. This enables us to diagnose certain infections. There's also many therapeutic applications within the pharmaceutical industry. And this is something that's particularly growing quite fast, following on from the COVID pandemic. Here we could be using oligos for gene therapy, where within our oligo we encode a functional version of a gene. We're then able to deliver this oligo to the patient to restore function of an otherwise mutated gene. So we could be using this to treat cancers, respiratory diseases, or rare genetic disorders. We could also be using oligos to help fight off viral and bacterial infections by either promoting the immune response or inhibiting a certain viral factor. So how do we actually create these oligonucleotides, either in-house or at these larger external parties? And we do this using an automated oligonucleotide synthesizer. Here on the right, you can see an example of this. And this is the Mermaid 12 by LGC. It's a very popular model, and many labs do use this, but there are many other options here. There are a few different techniques for doing oligosynthesis. Synthesis via solid phase through the phosphoramidite method remains as the most widely used method. in this method, what we're doing is we're adding a nucleotide monomer to a solid support via a linker. And in each cycle, we're adding a new monomer, new nucleotide, to this growing chain of oligonucleotides. And we do this in the 3 to 5 prime direction. Between each oligonucleotide addition, we'll do a wash step before addition of another specific nucleotide to build a specific sequence of nucleotides. So let's look at the synthesis workflow in a little bit more detail before we start looking at C&D. So here's an illustration of the phosphoramidite cycle. This is specific for DNA synthesis, but it's very similar in RNA synthesis. And what we can see is for each nucleotide addition, we have to perform 4 stages in this cycle. So firstly, distillation, coupling, oxidation, and then capping. Once we've finished this cycle, we can then add on the next nucleotide. We've animated these just so that we can see this step-by-step process in a little bit more detail. So firstly, we have our solid support there in orange, bound to our first nucleotide, in this case thymine, via a linker. The first stage in deprotration is removing the 5' protecting group. This enables the next nucleotide to come across in coupling and anneal to the first nucleotide. We then perform oxidation to stabilize this internucleotide linkage and form a stable backbone. The final stage is capping, and this is really important because 100% coupling of the nucleotides is impossible. We're always going to be left with some unbound 5' ends, as you can see on the right side there. If we were to continue the cycle with capping, the next nucleotide would bind to this T, thymine, regardless of missing the second cytosine nucleotide. And these are called shorteners. And to prevent their involvement in subsequent reactions, we cap them. And this terminates these shorteners so they are no longer extended. Once we've completed those 4 stages, we then cycle around to another round of deprotration and growing and nucleotide chain. So the end of oligosynthesis, this is what we're left with. We're left with our solid support bound to our specific nucleotide link sequence via a linker molecule. We also have protective groups that you can see in red on each of the nucleotides, and this so far has prevented any unwanted side chain reactions. After synthesis, we now need to perform cleavage and deprotection. So firstly, cleavage is we're cleaving the linker molecule, or linker group, to remove our oligos from the solid support. And secondly, sounds deprotection is just removing these protective groups, prevented these unwanted side chain reactions thus far. So at the end of C&D, we're left with our final product, which is remove all the solid phase and also the protective groups. This is now ready for downstream processing. So here we can see the entire oligosynthesis workflow. So it's starting with the synthesis that we've just been through, and then the cleavage and deprotection. We would then elute our oligos. So they will still be bound to the solid support via weak intermolecular binding, not via the physical linker. We can therefore just elute these oligos in a liquid solution, removing them finally from the solid phase. So that's the elution step. We would then perform quality control, purification, analysis, and we typically store oligos via freeze drying. And what I wanted to highlight in this slide is we can see for the synthesis step and all of the quality control steps that we're using modernized automated equipment is able to safely and quickly process the oligos. What's clear to see is that the elution step, cleavage and deprotection in particular, hasn't followed this trend. And this really remains the bottleneck in this entire synthesis workflow. It involves multiple labor-intensive steps. It's time-consuming and it can have safety concerns. So let's have a look at traditional cleavage and deprotection and how this is typically done in liquid phase. So here we're physically soaking our solid support-bound oligos in our cleavage and deprotection reagents. And this might be aqueous ammonium hydroxide, it could be methylamine, or it could be a mixture of both, typically a 1-to-1 ratio for amyl. And this is done by manually pipetting our reagents into either deep well plates or columns containing our solid support-bound oligos. As these reagents are all corrosive and flammable, serious care and PPE must be taken when handling these, particularly with us running with these solutions for extended periods at high temperatures. A lot of vapor is produced. Depending on the oligo type, a few different heating methods are applied. Typically, it's performed via conventional heating approaches, so hot plate or bath, at around 40 to 80 degrees. For somewhere between 4 to 8 hours for heated techniques, and then for our thermoliable oligos, we have to perform ultra mild C&D. We do this at room temperatures, and it can take anywhere between, say, 12 to 24 hours, so quite extended period. Once we've performed our C&D, we then need to evaporate off our reagents. This is quite a time-consuming step and can also cause degradation of our oligos. Once we've evaporated, we can then perform downstream QC. So just to recap on C&D traditionally and the limitations of this conventional approach. So firstly, it's the long reaction times, up to 27 hours with thermoliable oligos, and also we need to do an evaporation step at the end. At room temperature, the yield is particularly low for oligos. We can heat up oligos to speed this up, but that leads to the degradation of some oligos, particularly thermoliable ones. There's multiple stages in which we might introduce possible error. So there's multiple different C&D methods to choose from. It's quite easy to pick the wrong method for a particular oligo, causing either really low yields or degradation of that oligo. There's a lot of manual pipetting stages, and with that, we increase the risk of human error, contamination. It's also labor intensive, as it sounds. It requires a user and a lot of fume covered space to be manually pipetting and evaporating these reagents from the oligos. It uses a large volume of solvents and C&D reagents. We have to physically soak our oligos, and that uses quite a lot of volume, as you can imagine. And finally, to safety limitations, we're heating up particularly nasty reagents in a bath next to a user, so we need to be really careful with PPE and fume covered use. So now that we've covered the background of oligonucleotide synthesis, we've looked at the limitations of traditional C&D and how this remains as the bottleneck in the synthesis workflow. Let's have a look at Milestone's WavePrep system as a solution for this bottleneck. So here we're using automated gas phase, cleavage, and deprotection. If we go back to our workflow diagram, we can see that WavePrep sits nicely in that entire solution, fully automating cleavage and deprotection, so that now our entire synthesis workflow is automated, quick, and safe. So really revolutionizing the C&D and streamlining this entire oligosynthesis by removing the traditional bottleneck. So in order to achieve this and remove this bottleneck, Milestone set out to develop a system that achieved 5 central aims. And these aims are what enable us to streamline this traditional approach. So the first aim is that we wanted this to be fast and fully automated, away from manual pipetting, with as little user input as possible. We wanted high productivity as well as high quality of oligos. We wanted superior yield and reproducibility versus the traditional approach. We also wanted to improve operator safety, limiting exposure of these vapor reagents to the user. And finally, we wanted to make it really easy to integrate existing methods into WavePrep and hopefully simplify these methods, allow us to use more simplified reagent mixes and also reduce the amount of time and the amount of different methods for different oligos. So those are the 5 really central aims that Milestone used when designing this system. In terms of how they achieve this, we really have 2 core concepts. So Milestone are the market leaders in microwave technology all across science. And here we're using microwave power to really efficiently and precisely control the temperature of our reaction, protecting our oligos whilst increasing productivity. Alongside this microwave power, we're coupling this to a liquid phase to create a reactive gas phase. And this reactive gas phase is what's doing our cleavage and deprotection, rather than immersing our oligos in liquid phase. So those are the 2 core concepts of this system. I just play this. So we've now just got a short video. I think it's a nice way to introduce the system before we look into it in a little bit more detail. What you'll notice is that the lifting and closing the system is all fully automated. And we'll go through the typical run. So we're able to easily just introduce our columns or deep well plates, in this case, into our reactor. By pressing start on the terminal, automatically lowers our oligos into our 10-liter reactor. As this is a pressurized reactor, we do need to clamp our vessel shut. And this is the only manual stage of the entire process. An additional safety screen that we can close. The system automatically loads our reagents into the system, typically around 400 mil. Once the liquid reagent has been loaded, we then pre-pressurize either with nitrogen or ammonium hydroxide gas. During the run, we have full control of multiple parameters in the system, allowing us to be really careful in making sure we don't overheat our oligos and cause any degradation. At the end of the run, the system handles all of the cooling, venting, and purging of the system to remove any residual gas. After it's done so, it's then depressurized and able to open. Once we've completed this stage, our oligos have been cleaved and deprotected. They haven't been soaked in any C&D reagents, so there's no need for evaporation. We can move straight to elution. So I hope that gave you a nice little background, and we'll now look in more detail at each of these steps. So firstly, that's focused on the microwave concept. So here we're using a microwave reactor. We're using Milestone's patent single reaction chamber technology. Here we have a 1,500 watt magnetron to deliver this high density microwave power. It's guided via our waveguide to our 10-liter reactor. Here it can couple with our C&D reagents and create our gas phase. What we have, which is quite unique, is a cooling jacket that surrounds this reactor. This is really important because it allows us to really quickly bring our oligos back down to room temperatures after a run. And this is shown to remarkably reduce impurities by preventing any overshooting temperature and also preventing degradation. This is the inside of that sealed reaction chamber. And if we look at more the gas cleavage and deprotection concept, what you'll notice is our our liquid phase sits at the bottom here of our reactor, and it's actually pumped into the system via this sample holding rod, no contact with samples. The microwave energy then really efficiently couples with this C&D reagent and really vaporizing it quickly. And in doing that, this vapor phase is reactive, and it's what impregnates through deep well plates or columns via hydrophobic filters, and then forms C&D. And what's really important is that only the gas is contacting the oligos, not the liquid. Given the sensitivity of oligos, fine temperature control is really important, particularly for thermal ion oligos. To achieve this really sensitive control, we have multiple sensors within the reactor. Firstly, a pressure sensor, which detects the pressure within the reactor. This pressure will increase as we begin to create our vapor phase. We then have two different types of temperature sensors. The first one sits in our sample holding rod and sits within our liquid phase. And secondly, and most importantly, is our vapor phase sensor, which sits in the middle of our reactor. And this is really important because it helps us see what temperature our gas phase is. And this is really the temperature which oligos are exposed to. Because of that, this is our main parameter. This is what we control the system based off. We're able to use a PID algorithm to really sensitively control the microwave power that's administered, and able to make sure that the temperature of this gas phase is very precise and stable. There's multiple different sample holding options, and this enables a wide range of production scale. Firstly, at the nanomole scale, the system is compatible with 6 96 position deep well plates. This is ideal for sort of high throughput production of batches of many unique oligos. We can also work at the nanomole to micromole scale using a customizable PTFE holding plate, as you can see in the middle there. This PTFE holding plate allows us to position many, in this case 70, small to medium columns. For the larger scale production, at the sort of millimole scale, the system comes equipped with our 55 mil columns as well as our 750 mil columns, so really large scale. All of these configurations are really easily changeable by the user. It takes a matter of seconds or minutes to change between these different configurations. And we can also run with mixed configurations per run. For example, we could have 2 of our deep well plates. We could have 1 of our small to medium-sized column plate holders, and then we could have 3 times 55 mil larger columns at the top. So it's a really flexible system designed for ease of use and also the ability to swap and change between different production scales. You may have noticed with our larger columns that we have filters on either side. These are hydrophobic filters that are porous to our C&D reagent, but prevent water from entering. If water is to enter, it may cause premature elution of our oligos, something that we don't want, of course. And as you can see on this slide, we also have the option to use these filters on our deep well plate setups. As these filters don't come in contact with the oligo at any point, we're actually able to reuse them, which helps with keeping the green footprint in the lab. Also able to design custom sample holders, and this is really important, specifically people wanting to streamline the entire process. We can create sample holders that fit directly the columns that you used for an oligosynthesis or downstream elution. This means that we don't need to remove the resin or oligos from your synthesis column into a C&D column. We can just use the same one all the way through. So we're really flexible in designing these, and we'll do this with you. to find the best approach. So now that we've introduced the idea of gas-phase C&D, let's look at the benefits of it over traditional liquid-based C&D. So firstly, we're not soaking in liquid reagent, so evaporation is not needed, it's faster, and there's less risk of degradation and cross-contamination. Some traditional methods for some oligos require cleavage and deprotection to be performed separately. In WavePrep, all of these techniques, all of these oligos can be processed simultaneously. So we do cleavage and deprotection together as a single run. We're also, because of our superior temperature control, there are fewer different methods required regardless of the oligo type, reducing the risk of potential method error or selecting the wrong method. We often also observe higher yields, particularly for these complex thermolabile oligos. So there are a range of different benefits. Beyond speed, we've also got safety and ease of use. The aim of the system was to fully automate the process and revolutionize reagent handling and user safety. So let's look at how the functioning and control of WavePrep allows us to achieve these goals. So firstly, let's look at the automated operating sequence. So what you can see, as you've seen in the videos, is that everything's fully automated. The system automatically lowers the oligo down into a reactor. We then seal our pressurized clamps and press go. It'll then begin to pump our reagents into our reactor. Once it's filled, it will be pressurized, and we will begin to heat up our liquid phase. Microwave coupling allows us to really rapidly create our reactive gas phase and perform C&D. We then pump the reagent out of the reactor and perform purging to remove any residual C&D vapors that remain in the reactor, so we can maximize user safety. As a fail-safe, we also have powerful extraction sources within the exterior cabinet. So even after purging, if there is somehow any residual C&D vapors, this is fully exhausted away from the user. That accessory to the WavePrep is the pump station, and this is really integral to the automation of the process. This pump station handles all of the reagent handling for the process. So it loads the reagent from our supply bottle to the pump station to the reactor. It handles the purging of gases, and it's also involved in the removal of the reagents at the end of the process into the waste bottle. The supply bottle uses a universal GL25 lid. This is particularly handy because it means you don't have to decant from your reagent bottle into a specific pump station specific bottle. All you have to do is unscrew the lid and put on the pump station lid into your reagent bottle. We also have sensors in both of these bottles to tell you the limit of the waste and supply. The software continues to monitor the amount in each bottle and won't let you start a run if there's not enough supply left or there's any risk of the waste being too high and causing overflow. Many of our users actually reuse our C&D reagents, now able to still avoid contamination issues, but further developing sort of the green approach of microwave technology as a technique for the future. Both WavePrep, the pump station, as well as the individual supply and waste bottles are fully exhausted. This means that we can use a system either inside the fume cupboard or, importantly, outside the fume cupboard, which means it doesn't take up any fume space. We can just connect these exhaust lines to an overhead extraction line, for example. Here you can see on the right these GL25 specific lids that should fit onto the vast majority of commercially available reagent bottles. So let's look at the methods in WavePrep. So the reactor is initially filled with 450 ml of C&D reagent. It could be either of the three that we've mentioned, or any other ones for that matter. Once the reactor's closed, we pre-pressurize with around 6 bar of either nitrogen or reactive gas, ammonia gas. And we'll then heat the reactor up to 40 or 90 degrees, depending on the oligo, leaving us with a process time of somewhere between 30 and 60 minutes, depending on the oligo type. So much faster than the traditional approach. On the line of user-friendly, we've got a really nice software system that enables full control of the system, live temperature traces, full export options into multiple file types, a built-in library of methods, and access to application reports and maintenance techniques. It's also 21 CFR Part 11 compliant, different access levels, and full traceability. So it's really important to the pharmaceutical industry. I just wanted to show you the temperature trace that we're able to see from this system. And as you can see, we can see a live trace of all 4 of our temperature sensors and pressure sensors, as well as the microwave power. And what's really important is our T1, this red line here. We can see at the start of the run, we apply a lot of microwave energy, black boxes, to get this to our target temperature. We've reached that target temperature within 10 minutes, nearly. It's then really important that we modulate the microwave power to really delicately hold the temperature at this temperature to prevent any degradation. And we do this by modulating the microwave power, as you can see by the step increase and decrease in microwave power usage. But just to conclude with a few benefits, we've sort of checked in on the benefits on the way, so these shouldn't be a surprise to you, but we're presenting WavePrep as a fast method that's able to deliver enhanced throughput. There's no evaporation, we perform C&D simultaneous, and there are fewer methods for all different types of oligos. Safety is drastically improved compared to traditional methods, as well as full automation. So there's no user exposure to chemicals, even outside the fume hood, and reagent loading and unloading is completely automatic. We're able to achieve better results due to superior temperature control and removal of the risk of cross-contamination, even with complex oligos with tricky protective groups and linkers. And finally, we've ensured really easy implementation. We're able to transfer methods from traditional approach to WavePrep really easily and with enhanced results. And just to finish, it's very easy for us to sit here and say these benefits. What's important and something that we like to focus on is actually seeing these benefits in action and trying to get some data from it. So I've got 2 case studies that I'm going to run through, which illustrate the benefits with a bit more data. So in the first case study, I'm going to be comparing conventional C&D techniques against WavePrep. I'm sort of highlighting the ease of transferring different methods to the WavePrep approach. These results were produced by one of our reference customers, LGC in Denmark. During their validation process of the WavePrep, they wanted to test the difference between their traditional methods and the methods in WavePrep. And that's what we've got here. So if we look at the oligo column on the far left, we're dealing with 5 different oligos, all of the same sequence, but different modifications. The first 2 here on the top left of your screen are using 2 different types of linkers. The bottom 3 are all the same oligos again, but they're modified with different fluorophores and quenchers, but the same linker type. And what we observed, what LGC were having to do traditionally, was they had a series of different methods for each of these different oligos. They also had extended processing times, ranging from around 3 hours to 8 hours. What we were proposing in the WavePrep during the validation process was the movement towards ammonium hydroxide, so only this one reagent mix, and only 2 hours processing time at 70 degrees. If we now look at the results, they're really encouraging. So not only can we see the yield is comparable, if not higher, in WavePrep in comparison to traditional approaches, we also see the purity is comparable compared to the standard method. And LGC, we're really happy with these results, and it validated their move from traditional C&D completely to WavePrep. They're one of our main users, which is great to see. We've got a full application report that we've written in collaboration with LGC. It's a really nice resource that breaks down the method in a bit more detail than I've gone through today. If it's of interest, please do reach out. We'll be more than happy to share it with you and talk you through it. The second case study that I wanted to talk us through is the idea of using WavePrep to shift from complex reagent mixes designed for really sensitive oligos to more standardized reagents without having an impact on C&D quality. So here we're looking at something called a GalNAc conjugated small interfering RNA. It's a real mouthful. Some of you will understand it, some of you will not. Essentially, this is a therapeutic oligo, small interfering RNA. And this GalNAc group allows us to target this oligo to the liver. This is the target site for this therapeutic oligo. Once at the target site, this small interfering RNA, which is just this oligo sequence, is able to induce mRNA degradation, or in other words, silence the expression of a particular gene in the body. And it does this in a sequence-specific manner. So this sequence here, in one of the strands, is able to target it to the mRNA and cause degradation of that mRNA, so the gene is not expressed as much. In this case, the siRNA that we're looking at is one that's able to target HPRT, which is a gene that's a housekeeping gene or enzyme that's expressed in the liver. The diagram at the bottom shows the different modification events on this oligo. As you can see, this oligo is complex and highly modified, and that makes it particularly sensitive. It requires very particular sensitive conditions and a mix of specific reagents. So here again, similar as we were breaking it down before, we're looking at 4 different oligos. NT stands for non-targeting. This is a negative control for the study. It's not targeting a gene. This siRNA is not targeting a gene. HPRT is obviously the oligo or siRNA that's targeting the gene in the body. And we then have 2 different kinds for each of the controls. We have the passenger strand, which allows us to bind onto this GalNAc conjugate. And we also have the guide strand. The guide strand is the strand which actually carries out the gene silencing, and these form a double-stranded RNA molecule. What we can see for each of these using the standardized method is not only is the process time very long because these are thermosensitive, around 18 hours, we also have to use different mixes beyond traditional ammonium hydroxide reagent. So we're using a series of different reagents there. When we look at it in WavePrep, similarly, we're massively reducing the process time down to 4 hours. We're also simplifying the reagents that are used. So we're just using ammonium hydroxide. There's no requirement for additional reagents with potentially additional safety concerns. If we go to compare the results once again, and what we see here with these 4 different oligos is that the WavePrep yield is in fact higher than the standard method, significantly so. The purity again is also significantly higher, and this is due to WavePrep's gas phase approach being more efficient to the liquid phase, and also the really sensitive temperature control that we're able to carry out with WavePrep. Finally, just wanted to look at some LC-MS data between liquid phase cleavage and deprotect oligos versus oligos that have been cleaved and deprotected in WavePrep. And what's clear to see is that you can notice that the oligos aren't fully deprotected with the liquid phase. We're seeing sort of side groups, and also the peak is less defined, and we're seeing some smaller peaks around it. Similarly, there's a bit of degradation, and we're seeing additional peaks that aren't present in WavePrep. So this data highlights what we saw on the previous slide, that we've got not only have we got increased yield, we've also got better quality cleaved and deprotected oligos with less risk of degradation. Just to summarize on this case study, WavePrep allowed for increased time saving significantly from 18 hours to 4 hours, increased yield, simplified method development, the need for simple reagents and one standardized method, whilst no sacrifice of quality observable by that LC-MS data. And this is the case even for complex, highly modified oligos, such as this HPRT targeting siRNA. Thank you very much, everyone, for listening. I hope you found that interesting. I believe Hemi's still around if there's been any questions.
Yep, thanks for that, Alex. Really informative webinar there. I will just check if we have any questions in the question box. Give everyone a chance to write any questions if they have any.
Of course, feel free to get in touch later on after this webinar if you have any questions that spring to mind. I'm more than happy to get a quick chat and talk through particular things that might be of interest.
Yeah, it doesn't look like we've got any questions this morning, Alex. So thank you very much for that. As mentioned, this recording will be available later on. And like Alex mentioned, any questions, please feel free to get in contact. Thank you all.
Thank you all. Bye.
Bye-bye.